Hello, everyone, and welcome to our ECOM seminar today. Before I introduce Colleen, I want to say that we will be using Slido as the interface or application to ask questions and participate. If you are not familiar with Slido, you can scroll down the web page where you are right now, and you can see the Slido interface. Questions can be asked at any time, which is nice, and during the presentation, and Colleen will read the questions and answer them at the end of the presentation. With that, I am extremely happy to introduce Colleen Baublitz. Colleen is currently a PhD candidate in environmental science at Columbia University. She is working with Dr. Arlene Fiore. Colleen's dissertation focuses on variability in tropospheric loss processes from polluted to remote regions. Previously, she received a master's in environmental engineering from the University of Florida, where she collaborated with Dr. Baron Henderson on a thesis investigating nitrogen deposition impacts from a range of potential climate mitigation scenarios. Along the way, she has been working to support the next generation of students and scientists. For example, she coordinated several outreach activities, including for Columbia's Girls in Science Day, using the NCAR-developed interactive activity on nitrogen deposition. With that, Colleen, please take over. Thank you.
Okay, thank you so much, Ivan. I really appreciate the opportunity to be here and to share my research with you all. I really appreciate also the seminar coordinators and the production team and their effort in organizing this. Thank you so much. Could I just confirm, can you all see my webcam? For some reason, it's sort of not showing up. Okay.
Yes, we can see it.
Okay, cool. Okay, great. Okay, thanks so much. Okay, so the project that I'll be focused on here is part of my dissertation. And so we're looking at insights into hydroxyl variability over the remote troposphere. Okay, and so one of the reasons that we're interested in this, so the hydroxyl radical, or OH, links methane and ozone, which are two of the most influential near-term climate forcers. And so here I'm showing a figure from the IPCC AR5 report in terms of the well-mixed greenhouse gas components of radiative forcing. And so I want to call your attention to methane. And so one of the reasons why methane is such a potent greenhouse gas is it's also a precursor to another greenhouse gas and air pollutant, tropospheric ozone. And so that's shown by the turquoise part of this plot. Okay, and so to give you a very broad overview of some of the chemistry that links methane and ozone through the hydroxyl radical. So ozone photolyzes to produce OH, which can then go on to react with methane. And so it's actually the primary sink for methane. And as part of that reaction, or the products of that reaction, are several hydroperoxy radicals that given that NOx is available, can then go on to produce more ozone and sort of start the cycle again. And so this just sort of gives you a sense for how OH is really critical in terms of linking these two really important constituents of atmospheric composition and climate. Okay, and so from there, as the primary methane sink, uncertainty in OH variability hinders our capacity to attribute recent methane trends. And so here I'm showing a plot of trends in methane emissions from 1980 to 2015. And so I want to call your attention to the green lines in this plot. And so these are representing the global trend in methane emissions. And so the dashed line is representing the most likely solution from an inversion. So sort of given our, that's our best guess at what methane emission trends would have been from year to year, where the solid line is showing if OH concentrations were held constant. And so in particular for the period of methane stabilization, which was from 2000 to 2005, we can see the role that OH concentrations had in terms of our estimate of methane emissions. And so at present, we would need certainty in our total uncertainty in terms of year-to-year trends in methane emissions would need to be close to 4%, but uncertainty in interannual variability in OH is closer to 7%. And so we can see from that this represents a tough part of our picture in trying to get a better sense of how methane emissions are changing and where they might be coming from towards regulating them. Okay, and then beyond that, we also see a large spread in modeled OH, which implies not just that there are differences between models in terms of OH variability, but also in terms of the OH sensitivity to its drivers. So that suggests that there might be something that we don't quite understand in terms of the factors influencing OH. And so we can see that from this figure. And so this figure is showing global average OH concentration across a series of chemistry climate models, which are each represented by different colors in this plot. And so these are the trends in simulated global average OH from the pre-industrial era from 1850 to present. And so one thing to note is that each of these model simulations were run with the same emission scenario. And so the rather broad spread across OH, as much as close to a factor of 2 between the lowest and the highest values, and also the differences in trend between the models suggest that there might not just be differences in the representation of OH itself, but also its sensitivity to its drivers. And so at present, existing proxies for OH reflect its global or hemispheric variability, but it would be helpful to have a higher frequency proxy towards bridging the relatively fine resolution observational constraints that we have for our global models, which are generally simulating much larger spatiotemporal scales. Okay, and so toward that aim, here I'm assessing 2 potential proxies for high frequency OH variability by combining some novel airborne observations with chemistry climate model simulations. And so first I'll be looking at a potential proxy that leverages steady state OH chemistry, broadly the ratio of OH production to its reactivity, which is represented in this slide with the K prime OH term, as well as formaldehyde, which is an intermediate product of the methane and OH reaction. And so first I'll consider the steady state proxy. And so to give you a sense for the observations we're using here, we're using measurements from the NASA Atmospheric Tomography or ATOM aircraft campaign. And so this campaign included a very comprehensive payload, in particular related to OH chemistry. And so it offers a really nice opportunity for us to assess these potential proxies. And so here I'm showing the horizontal flight tracks on the right. And I also want to note that as the plane is flying along these tracks, it's flying up and down to sample the vertical extent of the troposphere. And so each of the variables it measures, there's also a nice vertical profile in addition to capturing this really broad spatial scale sample by ATOM. And so we're interested in really background pristine chemical air masses. And so we filter for parcels that might be influenced by fire or by stratosphere. And in particular, in the case of formaldehyde, both formaldehyde and OH are sensitive to changes in sunlight. And so while formaldehyde might still reflect OH variability at low sun, that relationship could look quite different from the rest of the ATOM campaign, which could affect our correlation analysis. And so we filter for low incident sun or high solar zenith angle. Okay, and so first, in considering the steady state proxy, so what we're looking for here is to what extent can we simplify OH steady state relationships in order to capture the variability of OH. And so this concept is based on past modeling studies, but notably these modeling studies focused on much larger spatial or temporal scales. Certainly they both focused on global average OH concentration, and some focused on really large temporal scales, in fact, from the last glacial maximum to present. And so towards our goal of looking for higher frequency OH proxies, we want to see to what extent this might hold over the very small spatial scales that were sampled by the ATOM campaign. Okay, and so to give you a sense for the drivers at hand here, so again, ozone photolyzes at the rate JO singlet D to produce O singlet D, which can then react with water vapor to form OH. And OH cycles with the hydroperoxy radical based on the relative abundance of NO and the sinks of OH, which are volatile organic compounds, over the ATOM flight tracks. That's principally methane, as well as and also, sorry, another sink for OH is through carbon monoxide. That's in fact its primary sink. Okay, and so one thing I want to note about the timescales that are at play here. So the species that contribute to OH production generally have lifetimes relative to that production that are much shorter than those that contribute to its loss. And so while the lifetime of NOx or ozone relative to OH production might be on the order of minutes to weeks, that of CO or methane relative to OH loss are on the order of months to years. And so what we're taking from that in the context of our analysis is that these production terms are probably more likely to be relevant on smaller spatial or temporal scales than the OH loss processes. Okay, and so broadly, to turn your attention to the big relationship sort of in the middle of this slide. Oh, sorry. Okay, so broadly, we anticipate that on the smaller spatial scales that ATOM sampled, OH will reflect its variability in its production, but that'll be modulated by its reactivity, that K prime OH term. Okay, and so one thing to note is that while the ATOM campaign included an OH reactivity instrument, OH reactivity was generally below the limit of detection for that instrument in the ATOM campaign, and in particular in the free troposphere. And so our approach instead is to calculate methane reactivity in relation to an inferred form of OH reactivity, which we approach based on OH steady state chemistry. And so we calculate the OH reactivity as the ratio of its production to OH concentration. And so we actually have what we need from the ATOM observations to calculate its production, which really I think goes to show what an exciting and comprehensive data set this is for studying OH. And so, to the extent that we include outside information, we're essentially supplementing the observations with rate constants from JPL. Okay, and so going on to look at this relationship in the 10-second ATOM observations with the ratio of OH production to methane reactivity, we see that this proxy broadly captures variability in OH concentration across the ATOM flight tracks. And so we see that here in that there is a slope, there is a correlation coefficient approaching 0.6 in the relationship between the proxy and OH concentration. And so what I also would like to illustrate with this slide is that the slope of this relationship is modulated by the relative contribution of methane to total OH reactivity. And so that's what's shown in the colors in this plot. Okay, and so something else that we sort of we can take from what we're seeing in terms of the broader relationship between the proxy and OH is that the slope seems to suggest that the mean contribution of methane to OH reactivity along the ATOM flight tracks is about 12% of its OH reactivity. Okay, and so this sort of begs the question, if we were able to subset for the relative contribution of methane to total OH reactivity, could we recover a stronger relationship between the proxy and OH? And from there, maybe use the proxy to try and learn something about the sensitivity of OH to its drivers. Okay, and so we move on to do that. And so here I'm subsetting ATOM for between 0 to 10 kilometers. And also for the contribution of methane to its total reactivity. And so I subset it for between 0.1 and 0.2 of a fractional contribution. And so we see that we recover a rather strong relationship between the proxy and OH. In doing that, the R squared now approaches 0.9. And we see we still have a rather large sample size that we can use to try and learn something about how OH is varying. Our sample size is close to 6,000 points. Okay, and so I just want to mention that one thing that's useful about using methane reactivity in contrast to some of the potentially more spatially variable contributors to OH loss, which include CO or other kinds of VOCs, is that the contribution of methane to OH reactivity, we find its variability to be rather spatially consistent. And so what that means in our case is that the proxy, even after subsetting for this contribution from methane reactivity to total OH reactivity, is that the proxy is still retaining rather broad spatial coverage following that subsetting. So that's nice, and we can sort of look at how the proxy relates to OH then in terms of maybe smaller spatial regions or perhaps seasonally, but I don't necessarily go into that here. Okay. And so, excuse me. And so what we find is that, and so from here, what we do is we essentially calculate sensitivity versions of the proxy where we hold individual processes or terms that go into the proxy calculation at their campaign median value. And so by comparing the relationship between the full proxy and OH with the sensitivity calculations of the proxy and OH, we can try and learn something about which processes or terms are contributing most to the relationship that we're seeing between the proxy and OH. Okay, and so here I'm showing, this is essentially using the same data set that I showed on the last slide, ATOM between 0 to 10 kilometers and subsetting for the fractional contribution of methane to OH reactivity. And so first, I am breaking this relationship down by looking at each of the individual processes that are contributing to it. And so one thing maybe worth noting here is that I've looked at this also including additional OH production processes, like for example, the photolysis of hydrogen peroxide. But I find that those terms don't really contribute to the variability in the relationship between the proxy and the OH. And so just for the purposes of simplicity I'm presenting here, I've excluded them from this figure. But so we see that on this rather broad spatial scale that the sink term that we're including here, methane reactivity, is the most influential process in terms of the relationship between the proxy and OH. Then following that, we have the two production processes. And so it's not necessarily terribly surprising that the sink is the most influential, as we showed on, as we said earlier, we anticipate that these sink processes will be more influential on larger spatial scales. And also beyond that, to capture the full extent of variability in the production processes, we have to use more than one term. Right? Okay, so then from there, I go on to look at the individual terms that go into this calculation. And so this is basically recalculating the proxy, but holding an individual term constant, and then considering the change in R squared between that sensitivity proxy and the full proxy. And so here we see that across the full ATOM data set, which is essentially this is very broadly sampling the remote troposphere. We see that water vapor is actually the most important term or the most influential term over the proxy relationship with OH. Okay, and so one thing that might be interesting to note in the context of this result is that other recent research coming out of the ATOM campaign focused on its intersections with our current models is that when global chemistry climate models are run as sort of pseudo box models where they essentially they take the ATOM observations as input and hold those composition parameters constant at the observed values, they find that the largest contributor to the discrepancy between terms of interest like the methane loss rate and the ozone production rate is actually model generated water vapor. And so given that we're seeing a rather large sensitivity of the proxy to water vapor in the observations itself, this sort of leads me to wonder if that discrepancy in model generated water vapor could be contributing to the intramodel OH discrepancy that we also see. So perhaps something interesting to pursue in the future. Okay, and so then going on from here to look at regional scales in contrast to the last slide, which was showing the full ATOM data set. Okay, and so as we anticipated, the OH production processes in contrast seem to dominate regional OH variability across ATOM. And so here I'm showing essentially a 2-kilometer depth subset of the ATOM data set. And so I'm calling this the upper troposphere. Really what I'm defining as the upper troposphere is between 8 to 10 kilometers depth. Okay, and so I'm showing on the left here this same decomposition analysis where I break it down by process, where each of these points is showing, essentially the difference in R squared when I hold this process constant. Excuse me. And so before I go on, I just want to note with the scatter plot on the right that we see that even when we break down the troposphere into this smaller region, the proxy still seems to reflect OH variability quite well. Okay. And so going on from here to consider, what we can take away from this regional decomposition of the proxy, right? Okay, and so we see from the plot on the left that in the upper troposphere, HO2 plus NO is the most influential process in terms of the proxy relationship with OH. And then on the right, that NO is the term to which the proxy variability is most sensitive. Excuse me. Okay, but one thing maybe from there to note is that HO2 still is exerting some influence over the proxy relationship with OH. And so HO2 is a parameter within this analysis that essentially also has relatively sparse spatial constraints. For example, there's not really a space-based retrieval of HO2. And so what that means is if we were to attempt to apply other observational data sets to use this proxy in the upper troposphere, we would need to make some sort of assumptions about the HO2 distribution. And then from there, I was somewhat surprised that it turns out water vapor exerts almost as much influence over the proxy as HO2 in the upper troposphere. That was kind of surprising to me, and I think goes to reinforce the takeaway from the last few slides looking at the full troposphere, showing this rather broad sensitivity of the proxy OH relationship to water vapor. Okay, and so if we move on to look at this in the lower troposphere, which I'm broadly defining as between 0 to 2 kilometers depth, we see maybe a little hint of why this becomes a rather complex process for us to represent, in that there are a larger number of terms that we need to capture in order to comprise the full proxy variability. Okay, and so this similarly is showing, essentially the process-based sensitivity results on the left, and then the term-based sensitivity results in the middle. And again, just sort of to mention, the scatter plot on the right is showing that even in the lower troposphere, in this new region, that the proxy still shows a rather strong relationship with OH. So we feel okay about trying to decompose it here too. Okay. And so to look a little bit at what sort of some of the takeaways we have here. So we see from the process-based analysis that O singlet D and water vapor followed by HO2 and NO are influential in the lower troposphere, and that's not terribly surprising. That's been shown by past work. But so one thing that I found kind of interesting was that while O singlet D and water vapor is certainly the most influential term in this region, one thing that we see is that ozone and water vapor variability exceed the influence of JO singlet D. And so that seems to potentially conflict with past results that showed broadly that JO singlet D is essentially the most important term in terms of reflecting OH variability. But that being said, these ATOM observations were taken generally under clear sky conditions and certainly in the daytime. And so it might just be that when there's not necessarily this sensitivity to sunlight, that we see other chemical parameters essentially supersede the influence of sunlight in terms of variability in the OH radical. Okay, and so what I would like to do next in that context is consider the OH sensitivity in terms of a larger averaging period. And so to do that, I plan to bring in some model results that might help to clarify how this shifts when we consider, for example, a 24-hour average as opposed to sort of the subset of temporal conditions that the ATOM observations reflect. Okay, and so something that we hope to learn from here, maybe also just to take a step back as far as the implications of this work. And so we hope to gain insights into OH sensitivity to its drivers over regions that show a large model spread. And so this figure is from a recent paper that looked at trends in OH across the CCMI models. And so we can see rather broad regional discrepancies. But something that jumps out to me is sort of certainly a discrepancy in the southern hemisphere, but in particular in regions of biomass burning or biogenic outflow. And so one thing that's exciting is the ATOM campaign certainly took very nice samples of these regions. And so it would be really nice to decompose the proxy over these regions and in comparison with what the CCMI models are showing towards trying to learn something about what might be driving the intermodal OH spread. Okay, and so my takeaways so far from the steady state proxy analysis are that using the ATOM observations directly, we can capture OH variability across several tropospheric regions. We find that the proxy seems to be sensitive to water vapor throughout the troposphere, even as far as into the upper troposphere. And then beyond that, the proxy can offer us insight, or rather more broadly, the proxy can offer us insight into the local sensitivity of processes that control OH with terms that are generally measured in space-based retrievals. And so that could be a nice future application of this work. Okay, great. And so from here, next, I would like to dive into looking at formaldehyde, which is an intermediate product of the methane and OH reaction, and so might be especially helpful in telling us something about OH variability in the context of methane oxidation. Okay, and so formaldehyde, again, is produced through the oxidation of VOCs, with methane being the primary contributor over the flight tracks that ATOM sampled. And so formaldehyde is lost itself either through oxidation by reaction with OH, as it's also a VOC, or through its photolysis, which I'm representing here by the rate J formaldehyde. And so one thing maybe worth noting is that we find that over the ATOM flight tracks, the vast majority, roughly 80% of formaldehyde is lost through photolysis. And so in that way, there should be a relatively linear relationship or direct relationship between OH fluctuations and those of formaldehyde. Okay, and so to give you a sense for where formaldehyde could fit in terms of our observation versus model analysis. So what we know of OH comes from rather fine scale observational studies, either laboratory studies or field campaigns that represent essentially a relatively small scale place in space and time. And so we need to use those observations to constrain our global models. But often these global models are representing, certainly much larger spatiotemporal scales. For example, of course, an endpoint of interest is the methane lifetime, which is on the order of a decade, in contrast with OH, which is on the order of 1 to 2 seconds. And so formaldehyde could be really helpful towards that aim, as it's, of course, a product of the methane and OH reaction, and it has a lifetime on the order of several hours. And so here we test the extent to which formaldehyde fluctuations might reflect those of OH towards constraining global models, in particular in the context of methane oxidation. Okay, and so in fact, it has already been shown using the ATOM observations that fluctuations in formaldehyde columns reflect variability in OH tropospheric columns. And so I'm showing that in the figure here from a recent paper led by one of our collaborators on our own project. And so here we see that ATOM column observations of formaldehyde reflect those of OH, in particular when OH is normalized to, or is essentially divided by the formaldehyde reactivity. And so to give you a sense for the chemistry underlying this relationship, on the right, I'm including sort of like a very simplified form of the formaldehyde steady state relationship. And so we see that formaldehyde is produced through the oxidation principally of methane along the ATOM flight tracks at a relative yield that I'm representing by this alpha parameter. And so in terms of the variability in this relationship, we anticipate that both the alpha and methane reactivity terms in this equation will be relatively constant over the ATOM flight tracks, so that we recover this proportionality between OH normalized to the formaldehyde reactivity and the formaldehyde concentration. And so what we're essentially attempting to do in dividing OH by the formaldehyde reactivity is to try to adjust for differences in the lifetime between OH, which again is on the order of 1 to 2 seconds, and that of formaldehyde, which is over several hours. Okay, and so this work was based on prior work that sort of laid the foundation for the theory in this relationship. And so And so this paper essentially asserted that at low OH concentrations, formaldehyde concentrations should reflect shifts in OH production. And so that's being shown in this plot where formaldehyde columns are related to differences in OH production, which is on the y-axis, and VOC reactivity, which is on the x-axis. And so I want to call your attention in particular to this region of low OH concentration. And so we can see here that the formaldehyde columns are essentially sensitive to changes in OH production. Okay, and so we anticipate that OH should be sufficiently low over the regions that ATOM sampled that it should hold, and this would be a nice place to test this theory. And so just to sort of reiterate or recall that species that contribute to remote tropospheric OH production generally have shorter lifetimes than those that drive OH loss. And so given that formaldehyde is reflecting, we anticipate formaldehyde is reflecting shifts in OH production, it should also reflect shifts in OH concentration, while OH loss, or really OH reactivity, is uniform. Okay, and so broadly, our objectives in studying formaldehyde as a potential proxy for OH variability is to combine these aircraft observations and our global model results to learn more about oxidation, and in particular across different spatial and temporal scales. And so the questions that we have here are, to what extent does formaldehyde reflect OH variability on spatial scales smaller than the tropospheric columns that have been shown in past work? And so here we focus, we essentially cut the troposphere, the ATOM observations, into 2 kilometer by 20 degree zonal bins to assess that. Excuse me. Okay, and so next we want to consider how the observed formaldehyde and OH relationships compare with an hourly simulation of the GFDL AM3 chemistry climate model, which we run at 2 by 2.5 degree resolution and sample along the ATOM flight tracks. And so to what extent is the model able to capture the spatial variability in that relationship? Then from there, we hope to use the model to help contextualize the ATOM observations. And so the next question we ask is, how does the model indicate that these relationships shift over longer timeframes? For example, here we consider daily timeframes. And so we hope that this can be a first step towards comparing the very fine scale ATOM observations with the spatial and temporal scales that are relevant for chemistry climate model projections, which are generally monthly or annually average values. And so what we're hoping to get at with that is, to what extent can we apply the ATOM observations directly to evaluate our chemistry climate models? Okay, and so I just want to give a quick introduction to the model that we're using, the GFDL AM3 chemistry climate model. And so there's certainly a lot on this slide. I'm going to let you go ahead and focus on whichever particular aspect of the model you might be interested in. But then, I'll highlight essentially the specific features of the model that we're using, or the modifications in our version. And so this model includes interactive stratospheric and tropospheric chemistry. It is on a cube sphere grid. It, again, is run at 2 by 2.5 degree resolution. It has 48 vertical levels. Our model, in addition to sort of what's shown in the diagram, includes gas phase and heterogeneous chemistry updates, as well as updates to the deposition parameterization. We use FastJX version 7.1 photolysis scheme. We're nudging to NCEP GFS reanalysis winds and using RCP 8.5 emissions. Okay, and so before I get into the observation and model comparison, though, I want to look at these relationships specifically in the observations. And so to do that, I use sort of a series of small subplots that I'm referring to as postage stamp plots. And so here I just want to sort of get you oriented to what's included in just one of those smaller subplots. Okay, and so in each of these subplots, the x-axis is a statistically normalized form of formaldehyde, and the y is similar for the OH concentration the OH concentration divided by the formaldehyde reactivity. And so we statistically normalize them just to better illustrate their dynamic range, as the dynamic range shifts quite a lot through the distribution of the troposphere. Okay, and so I'm showing here essentially the equation that we use to normalize it in case you're interested in it. But so each of these subplots represents a 2 kilometer by 20 degree zonal subset of the ATOM data. And so really what they're meant to represent, or what they're helpful in representing, is the distribution of the strength of relationship between formaldehyde and OH across the troposphere and across the ATOM data set. And so the background color is demonstrating the strength of the R-squared correlation coefficient between formaldehyde and this normalized form of OH. And so I just want to mention, sorry, I'm using normalized in 2 different ways, which might be a little confusing, but so I just want to mention that I calculate the correlation coefficient prior to the statistical normalization that I mentioned. And so the correlation coefficient represents the extent of correlation between the ATOM formaldehyde concentration and the OH concentration divided by the formaldehyde reactivity. So prior to that statistical normalization, which is really just done for illustrative purposes. Okay, and so basically we combine a bunch of these smaller subplots to get a relatively quick view of the distribution in the strength of relationship between formaldehyde and OH, which I'm showing a preview of in this plot on the right. Okay, and so in our case, in particular, we're focused on the remote troposphere between 2 to 8 kilometers depth. And so, sorry, maybe I should introduce this a little better. And so what the subplot is now showing is these 2 kilometer by 20 degrees zonal bins between 60 degrees south and 60 degrees north in terms of the X coordinate, or the horizontal space that this subplot is reflecting. And then in terms of the vertical shift, that's showing the full depth of the troposphere from the ATOM observation. So between 0 to 10 kilometers, but subset into these 2 kilometer bins. Okay. And so again, we're focused on 2 to 8 kilometers. And so that's based on some recent research that's already come out of the ATOM campaign. And so this research found that above 8 kilometers, prior modeling results underestimate ATOM OH, and that's at least, within the combined, it's approaching the combined uncertainty of the measurements that were used in that study. And then close to the surface, really in the marine boundary layer, some results, or some research has found that there is missing OH reactivity, likely from an unknown volatile organic species. And so we're really interested in the steady state chemistry that we have a little bit more confidence in terms of being able to infer OH concentrations. And so we focus here on more of the mid-troposphere between 2 to 8 kilometers depth. Okay, and so, excuse me. And so we find that as slightly differs from the past research that was focused on the tropospheric columns, that controlling for OH reactivity strengthens the formaldehyde and OH relationship on the smaller scales that we're considering in this study. And so what I'm showing in this plot is essentially, again, these 2 kilometer by 20 degree zonal bins, this time between 2 to 8 kilometers depth specifically. And so the scatter points in this plot are showing that they basically are demonstrating where the OH reactivity of that point falls within its distribution in that cell. And so again, I mentioned this earlier, but just to sort of quickly reiterate that we're inferring the OH reactivity using the ratio of our calculated OH production to the OH concentration, both from the ATOM observations. Okay, and so the white points in this plot are showing points with OH reactivity that falls within 1 standard deviation of its mean value. And so the orange points are showing basically more variable OH reactivity. And so we can see from this that basically if we are able to control for shifts or excess variability in OH reactivity, that we can better recover the relationship between formaldehyde and OH. And so just the white points in this plot, so essentially those within 1 standard deviation of mean OHR, are being used to calculate the correlations, the relatively stronger correlations that are shown here. Okay, and so what we take from this is that a better understanding of the OH reactivity distribution would facilitate OH inference via satellite retrievals of column formaldehyde over the remote regions that ATOM sampled. But that being said, again, the OH reactivity instrument measurement is quite challenging. That being said, it might be a nice area for future investment towards this goal of trying to learn more about the OH distribution. Okay, and so next we'd like to compare what we're seeing here with results from our chemistry climate model, the GFDL AM3 model, to see to what extent the model is capturing the relationship between formaldehyde and OH shown in the observations. Okay, and so here I'm showing essentially the same figure that I showed on the last slide on the right, but removing those orange points. And so this is including only OH reactivity within 1 standard deviation of its mean value. And so those are the observations on the right. And then on the left, I'm showing results from AM3 that are hourly averaged and sampled along the ATOM flight tracks in the exact same way as, so it's essentially in the exact same way as the observations. Okay, and so broadly, we see from this that AM3 demonstrates a tighter relationship between formaldehyde and this normalized form of OH in comparison with the ATOM observations. But one thing to maybe note from this is that these are representing rather different spatial and temporal scales. And so that's something that we need to consider in the context of trying to understand why these correlations might look a little bit different. And in addition, we hope to leverage the information that the model is providing us to provide context for the ATOM observations. And so we're hoping to use the model to develop some level of a transfer factor over the different scales that they represent. And so here I'm showing the relationship between formaldehyde and OH, similar to what I have been showing on the past few slides. But instead of the background color representing the strength of the relationship via correlation, here it's showing the slope of this relationship. And so it's more a comparison of the differences in magnitudes between these terms. And so we see that broadly in comparing the ATOM observations, which are on the left, with hourly model results, which are in the middle, and daily model results, which are on the right. Again, both of the model results are sampled along the ATOM flight tracks. We see that broadly, the model captures the spatial variability in this relationship that the observations are showing. But it seems that the slope increases as we go to higher temporal averaging periods. And so we're not really sure why that is right now, but it's something that we're really excited to dive into a little bit deeper as far as for our next steps for this project. Okay, and so what we plan to do next with this work is to interpret these distributions. We will evaluate the model representation of each of these specific processes that influence the formaldehyde-OH relationship. And then from there, attempt to parse the role of differences in their spatiotemporal scales, again, towards developing this transfer factor that could help contextualize the ATOM observations when applying them as a constraint on our global models. Okay, and so just to sort of take a step back and highlight a little bit about why this is necessary or why this is of interest. And so we see that across the CCMI models, the spread in OH concentration can lead to a 30 ppb difference in methane across these models over just the scope of 6 years, 6 simulated years. And so certainly we are in critical need of more constraints on OH for our global models in terms of understanding methane trends. And so here we hope to bridge the formaldehyde and OH relationship between these fine resolution observations and the global model spatiotemporal scales towards offering a new path forward for constraining our global models, in particular in terms of the representation of methane oxidation. And so our takeaways from this aspect of the project so far are that the ATOM observations demonstrate that across much of the free troposphere, formaldehyde correlates with OH, in particular when accounting for shifts in OH reactivity. And so that differs slightly when considering larger spatial scales, like on the scale of a tropospheric column. Okay, and so from there, we look at our model to see that the model broadly captures, but perhaps overestimates the strength of the observed formaldehyde and OH relationship. And then finally, what we're working on now is combining the AM3 results and the ATOM observations to quantify the shift in the formaldehyde-OH relationship to bridge the differences in the observed and modeled spatial temporal scales. And so this work, in particular, the formaldehyde piece, I'm presenting at AGU. And so if you are interested and would like to learn more, please, feel free to look up my talk, or I'm also happy to send you my talk. And so I'm participating in the live Q&A session for this section 82 on December 10th, which is rather early in the morning in terms of mountain time. And so I'm certainly also happy to answer questions over email if you might have any. But okay, so broadly, so this is sort of my last, wrap up conclusion slide. And so here we're combining novel airborne observations and results from our global model to try to learn more about methane oxidation. And so we showed results for 2 potential OH proxies, the first related to OH steady-state chemistry, which seems to be helpful in terms of learning a little bit more about the sensitivity of OH to its drivers. And so we're finding so far a rather robust, at least spatially, sensitivity to water vapor. And so our next steps for that project will be to bridge these observational results with models to assess this influence on varying timescales towards hopefully sensitivity constraints on our global models. And then from there, we looked at formaldehyde, which could be in particular helpful in terms of constraining model methane oxidation. And so we see that on essentially smaller scales than have been considered in past work. Formaldehyde does reflect OH, in particular when accounting for OH reactivity. And so we also see that our model, AM3, the chemistry climate model, seems to mirror spatial variability and the magnitude of the formaldehyde OH slope, so that there's initially promising results that the ATOM observations could be used directly as constraints on our global models. Great. Okay, thank you so much. I should say, I'm so sorry, I meant to mention this earlier, but I actually came to NCAR in 2018 for an atmospheric chemistry and aerosol modeling workshop that I know some folks put a lot of work into organizing, and it's been extremely invaluable information as I've made progress or worked on my dissertation. And so I just, want to take this opportunity to just say thank you so much to the folks at NCAR who, put such nice work into running that. I really appreciate it. And it's been super helpful for me in terms of pursuing my dissertation research. Okay, thank you. And thank you again for this opportunity to present.
Okay, yeah, thanks, Colleen. Very nice presentation. Extremely useful, I think. Can we share the Slido questions now? There is one question. Can you read it, Colleen?
Oh, yeah, okay. Oh, okay, I see. All right, sorry, I thought I should look it up separately. Okay, great. Okay, let's see what this is. Sorry, I gotta move my thing. Okay, so the question is, AM3 formaldehyde to OH is much stronger in Northern Hemisphere than Southern, but this is not necessarily what's going on in the observations. What's going on here? That's a good question that I'm not 100% sure of right now. So one thing that I think we saw across the chemistry climate models is that it seems the Southern Hemisphere is maybe not necessarily as well constrained in terms of our model representation of the oxidation process or the process of oxidation. And so, I think for one, I'm sure that, other folks from the ATOM campaign have more insight to this, but might have a similar conclusion that it seems, the Northern Hemisphere, to my mind, looks surprisingly different than the Southern Hemisphere, given, how far distant from source regions, those observations were taken. Anyway, there could be some really interesting insights there. I think that's a really nice question, and I look forward to trying to parse that a little bit more. Thank you for asking, Olivia. Oh, some really nice questions. Okay, great. Okay, so Louisa asked, what measurements might help answer some of your remaining questions? How would you redesign ATOM if you could do it again? Okay, I think that's a great question. I think having more insight into, in particular, the oxidative processes, and And so I think something that has been really difficult is essentially trying to learn more from the OH reactivity aspects of this work. And so, I don't know to what extent this is technically feasible. Right now, it seems like it's quite challenging. But I think it would be really nice to be able to have some level of breakdown of the OH loss processes in particular, in terms of the more variable components, which I think include some of the non-methane VOC species. Okay, I think that would be really helpful. Thanks for asking. Okay. So Louisa has another question. That's also very nice. So have you considered running the model at higher resolution to closer match the observations? And so that would be really nice. I don't currently have the capacity to do that with at least the version of the model that we're using. But something that we are going to try and do is to resample the observations so that they might better bridge the differences in temporal scales between the 10-second observations and the hourly model results. And so previously I was looking at, I think, 2-minute resampled, and that seemed to be fine in terms of still capturing the differences in variability. And so I might try and test the limit of resampling the observed data to try and get a better sense for how those relationships shift over larger temporal averaging periods as we approach modeling scales, but hopefully without losing too much information about what's included in each of those or rather what's included across the 10-second observations. Okay, thanks, Lisa. Okay, great. Okay, so next is from Eric. Okay, what is the effect of uncertainty in the formaldehyde observations in developing relationships with methane oxidation and OH variability? Okay, that's a really good question. Okay, yeah. I think that's a really good question. And so as it stands for right now, I think that the observations offer a really nice constraint in terms of our global models. But I know that there are differences in formaldehyde, in particular, across instruments, and certainly in the context of the differences in magnitude, right? The slopes that we were showing and the relationship between formaldehyde and OH, I know that likely will differ between instrument applications. Okay, and so I'm sorry, I think I might not, maybe if I could ask for more information about the particular, in terms of if there's a particular feature, I guess, of the implications for the uncertainty in the oxidation and OH relationship. I'm not sure to what extent my answer was helpful, but if I could ask for clarification or help clarify that could be helpful. Thank you for the question in any case. Okay, and so the next question, okay, it's from Benjamin. Okay, so for the first part of your talk, why did you not investigate the role of CO, which is the largest OH sink? Okay, so that's a great question. I wonder if I could, is it okay if I go back to my slides to show? Thank you. Okay, so I have some extra ones here. Okay, so, okay, I didn't show this. I don't think that this, necessarily underpins our results, but hopefully helps offer context. And so in addition to sort of what I've been showing here, we've been using results from the Foambox model, which were run with the ATOM observations as input. And so from these box model results, we have really nice estimates of the reaction rates of different processes that are relevant here. And so I'm essentially in this slide showing the breakdown of different contributors to OH loss. Okay, and so one of the reasons that we are focused, one of the reasons that we use methane in particular, beyond just our broader project goal of being interested in methane oxidation, is that the other reactive carbon contributors show much more spatial variation in terms of their contribution to OH reactivity. And so we can see that, for CO in particular, which as Benjamin, nicely noted is the primary sink for OH, varies between, 20% to as much as close to 60% of total OH loss. And so, what that means, hold on one sec, let me see if okay, maybe this is helpful. That wasn't what I was trying to go for, but maybe this can help get at it. And so what that means is that, because we take this extra step of essentially subsetting for the fractional contribution of methane to OH reactivity in order to recover that much stronger relationship between the proxy and OH before then decomposing it. What that means is that methane offers us a somewhat novel opportunity to essentially look at really broad spatial regions because its contribution to OH reactivity is so consistent. And so what I'm showing on this plot is essentially all of the ATOM observations colored by the contribution of methane to its OH reactivity on the left. And then on the right, I'm showing essentially just the subset portion that I included in essentially the proxy decomposition. So the fractional contribution where it's between 0.1 and 0.2. And so, what that means is that, so again, I guess this means that methane oxidation is relatively unique in offering us a way to look at much broader spatial regions, whereas, these more variable contributors to OH loss like CO and other kinds of VOCs that have a more localized influence over OH reactivity. And so maybe another way to say this is that you could use CO, but what it would look like, is that, if I subset, so going back to this one, and so, excuse me. And so if I subset, for example, for CO, around 50% of the fractional contribution, I would still see that really strong relationship between the proxy and OH. Instead of using methane reactivity, if I use CO reactivity. But, that would essentially restrict my spatial analysis to just sort of the region, this region of the troposphere, right? Where, CO shows that level of fractional contribution. Okay, I hope that helped answer it. Okay, and so I can stop sharing so we can go back to the slide. Thank you for the question.
I think, Colleen, that was the last question. I don't see any more questions. And just Eric April mentioned nice talk. So you guys can talk more offline if you want to. So
okay, great.
That's great.
Okay,
so,
thank you so much.
Yeah, I don't see more questions. Very nice talk, Colleen. I really appreciate it.
Thank you. Yeah, I really appreciate the opportunity to share my work.
Yeah, no problem. And thanks everyone for joining today. See you guys, everyone. Bye-bye.
Okay, thank you. Thanks, Ivan.